So now let us talk about the argument of complex number. As we had seen in the previous lecture as well, what basically is argument? Argument is the angle that our complex number is making with the real axis. So this x-axis here is basically my real axis, and this y here is my imaginary axis. And this together we call it as the Argand plane. Now this angle that it is making, now this angle is always in the anti-clockwise direction. So remember this thing, theta is positive when I'm measuring it from the anti-clockwise direction. Now let's say if I measure it from the clockwise direction, then it would become negative. So basically my theta is going to be b by a, or what else can I say about theta is that if theta is equals to tan inverse b by a, that means this can also be written as tan inverse of imaginary part of z upon real part of z. I hope you are understanding this thing. So for any type of complex number that we have been given, we can write it in this format also. We can find out your argument by writing this way also, tan inverse imaginary part of that complex number divided by its real part. Now one thing that you need to remember, if let's say theta is the argument of z, if let's say theta is argument of z, then we can say that 2n pi plus theta, where n belongs to integers, this would also be our argument, is also an argument. So basically what we are doing is we are taking a one complete turn of all of the quadrants, and then we are coming back to the same theta. So our arguments cannot only be just theta, it can be 2n pi plus theta. Now this is something that we learned in trigonometry as well, where whatever let's say theta has been given to us, what do we write our theta as? Theta plus pi theta or n pi. For sine, cos, it used to be different. So similarly for here, if we find out our argument to be theta, then we can say that 2n pi plus theta would also be our argument. Now again, when we talk about different quadrants, now in this quadrant, my first quadrant, always my argument is going to be theta. In my quadrant 4 also, my argument is going to be theta. However, in quadrant 2, it would change. It would become pi plus theta. And in my third quadrant, it would become theta minus pi. So keep this thing in mind. So basically what we are trying to say is that in my first quadrant and fourth quadrant, my argument is going to come out to be positive. However, in my second and third quadrant, it is always going to come out to be negative. Now this is what we call as the principal argument. Now you must remember one thing, that this principal argument always ranges from either minus pi to pi, where pi is included and minus pi is not included, or it can be minus pi to pi, where minus pi is included and pi is not included. Now here are a few properties of principal argument. Principal argument is the value of theta which is restricted in this range. Now it can be either this, or it can be in this format also, minus pi up till pi, where pi is not included. So principal argument means our value is restricted to only minus pi to pi. That means in my first and fourth quadrant, my argument would always be positive. In my second and third quadrant, my argument would be negative. Now let's say if I have z is equals to a, that means it is a purely real number. That means I do not have any imaginary part in it. That means it is going to lie in the real axis only. So my argument can either be 0 or it can be pi. So that is what has been written here. If a is greater than 0, my argument is 0. If a is less than 0, it can be pi or minus pi. I can rotate it. If I rotate it in the clockwise direction, it would become minus pi. Now let's say if I have z as a purely imaginary number, this would mean that my z is lying in the imaginary axis somewhere here. So if it is lying in the imaginary axis, that means my argument can be pi by 2 or it can be minus pi by 2 simply. And if z is 0, that means my complex number is lying at the origin only, at the origin itself. That means there is not going to be any argument for it. Of course, if z is 0, that means my modulus would also be 0. So if z is 0, my argument of z would be 0 and my modulus of z would also be 0. Now there are a few properties that you need to remember. Let's say if I have multiplication of argument of z1 and z2, two complex numbers, so I can separate it out as two different addition terms. Again, properties of logarithm that we had studied, we can apply those here in argument only. If it is in division, it would become argument of z1 minus argument of z2. Power property, argument of z to the power n can become n argument of z. And conjugate properties, of course, a argument of z to the power, z conjugate would become minus of argument z. So keep this thing in mind. Now let's look at this question. If z1 and z2 are complex numbers such that real part of z1 is this and real part of z2 is this, then the argument is also given to us, then imaginary part. So we have to find out the sum of imaginary part of these two complex numbers. So first what we'll do is, let us assume z1 to be x1 plus iota y1. I'll assume my z2 to be x2 plus iota x2. Plus iota y2. Now let me solve for the first equation where they've told us that real part of z1 is equals to modulus of z1 minus 1. So what would this become? What is my real part of z1? It is x1. x1 is equals to modulus of z1 minus 1. So this would become root under x1 minus 1 whole square plus y1 square. Of course, I'm subtracting 1 only to my real part because 1 is a real number. There is no imaginary part given extra, right? So it would become x1 minus 1 whole square plus y1 square. So let me square both these sides. This would become x1 square is equals to x1 square plus 1 minus 2x1 plus y1 square. x1 square gets cancelled out, and from here we get y1 square to be equal to 2x1 minus 1. So this is my first equation that I've gotten. Now let me solve for the other equation they've given us. Now for the other equation, they've given us the same thing. Real part of z2 is equals to modulus z2 minus 1. So of course I'm going to get the same thing, so I can directly write it down. y2 square is equals to 2x2 minus 1. So this is what I'm going to get from here as well. Now they've given us that the argument of z1 minus z2 is pi by 6. Now what do we understand from this? If my argument of z1 minus z2, wouldn't this mean that they are talking about tan inverse of imaginary part? What is my imaginary part going to be if z1 minus z2? For z1 minus z2, my imaginary part would be y1 minus y2. So this would become y1 minus y2. And tan inverse, below we used to have a real part, and my real part is x1 and x2. So this would become x1 minus x2. I hope you've understood up till this portion here. Now in this entire equation that they've given us, you can see that there are values y1 minus y2. So simply the equations that we've gotten in through our first simplifying, what we can do is we can subtract it and try to frame y1 minus y2, and then we'll put this value of pi by 6 there. So what I'll do is, if I consider this to be my equation 1, this to be my equation 2, what I'll do is I'll do equation 1 minus equation 2. So from here we'll get y1 square minus y2 square. This is equals to 2x1 minus 1 minus 2x2, and this minus 1 would become plus 1. So this and this gets cancelled out. Here we would have y1 plus y2, y1 minus y2. This is equals to 2 times of x1 minus x2. So from here what we can see is y1 plus y2, this is equals to 2 times of x1 minus x2 upon y1 minus y2. Now what was asked to us in the question? Basically we had to find out the sum of imaginary part of z1 and z2. So what would be the sum of imaginary part of z1 and z2? It would be y1 plus y2. So that is exactly what we've gotten. Now simply what we'll do is we'll replace the values of x1 minus x2 and y1 minus y2 from this argument equation and then solve for our answer. So if we know that y1 minus y2 upon x1 minus x2, this is equals to tan pi by 6. That means what is this value going to be? y1 minus y2 upon x1 minus x2. This would become 1 by root 3. And if this value is 1 by root 3, if I replace it here, this would become 2 root 3 basically. And here you can see y1 plus y2. This is exactly what we had to find out. So this becomes my answer. Of course, here there is a reciprocal, that is why 1 by root 3 became simply root 3, and multiplied by 2 we get 2 root 3. So again, a very simple question. So one thing that you need to keep in mind while solving questions is that whenever, let's say if you're not being able to find out certain property or certain identity through which you can directly solve, the best way to solve such complex numbers is that you assume your complex number to be x plus iota y and then try to solve the question. So now we'll study about the different forms of complex number, the forms of complex number that are available. So till now, the form of complex number that we were studying, where z is equals to x plus iota y, it was known as the Cartesian or the rectangular form, where a used to be our real part and b used to be our imaginary part. Now there's other way of representing the same equation, which is the polar form. How do we write down our polar form? We write it as z is equals to r times of cos theta plus iota sin theta. So what is r here? R is basically my modulus of z and theta is my argument. So that means you can see that polar form is a much better form than the Cartesian form, because here I can directly see what my modulus is going to be and what my argument is going to be. And if I write it down in a better way, if I multiply the r inside, this would become r cos theta plus iota r sin theta. So from here I can say that this would be my real part and r sin theta would be my imaginary part. That means polar form is a much better form for me to represent my complex number. So this is how it is generally represented. Now there is one more form, exponential form, which is also known as the Euler form. It is represented as z is equals to r e to the power iota theta, where again theta is my argument and r is my modulus. Now if I try to compare my Euler and polar form together, what would I get? E to the power iota theta is equals to cos theta plus iota sin theta. So this is one relation that you must remember, because this comes a lot in handy while solving questions where you have been given a complex number to the power n and it becomes very difficult for you to solve. That time what you can do is, let's say if I have z to the power n, so simply what would happen is I'll convert it into Euler form. So z to the power n can be written as r to the power n e to the power iota n theta. And if this is n theta, this portion is n theta, how can I write this down? This can be written as cos of n theta plus iota sine n theta. So my argument would basically become n theta. So keep this thing in mind, that Euler form comes in handy when you have to solve complex numbers which have been given of high powers. Now if I was to show you the proof of how we are getting our polar form, what was my polar form? Z is equals to r times of cos theta plus iota sin theta. So if you look at this, again here my x-axis is the real axis and y-axis I'm considering it to be my imaginary axis. Imaginary axis. So from here you can see that this length here, p, its distance from the origin is my modulus z, which I'm calling it as r. And if this is r and my argument is theta, wouldn't this distance OM, wouldn't this be r cos theta as per the triangle properties? And wouldn't this distance be my r sin theta? So basically that is exactly what we've represented in the polar form. We've written our z as, what is my real part here? My real part is r cos theta. And what is my imaginary part? My imaginary part is r sin theta. So that is how you get your polar form. So keep this graph and the form in mind. Now talking about the Euler form or the exponential form. Now here you can see that theta, sorry, here they have given us phi, you can consider it to be theta. Here theta is my argument and this length, entire length here is my r basically. So if this is my r, here I have my cos theta, here I have my sin theta. So wouldn't, if I consider this to be a part of a circle, wouldn't this point here be e to the power iota theta? So Euler form z can be represented as r e to the power iota theta. Now one important thing that you must remember is, if I try to find out modulus z, It is going to modulus of r e to the power iota theta. So this can be written as modulus r, modulus e to the power iota theta. And what is my modulus r? My modulus r is basically my modulus z. So this would become r into 1. That means what I'm saying is that e to the power iota theta, its modulus is basically equal to 1. So keep this thing in mind. Apart from that, one more important thing about Euler form that you must remember is, let's say I have e to the power iota theta, and if this thing can be represented as cos theta plus iota sine theta. Now what if I have e to the power minus iota theta? Now this can be represented as cos theta minus iota sine theta. Now if you were to ask me the proof of this, of course, what is my argument here now? My argument is basically minus theta. And if I put minus theta in place of my theta in cos as well as sine, my cos of minus theta is cos theta. So it can be written directly as it is. However, my sine of minus theta is minus sine theta. So that is why it comes in minus sign here. So keep this thing in mind about Euler as well as polar form. Now there's one theorem which is known as the De Moivre's theorem. Again, repeating the same things again. Let's say if I have z to the power n, this would basically be equal to r to the power n cos of n theta plus iota sine n theta. And how do we get this equation? By proving it from the Euler theorem. If I prove it by the Euler theorem, I can write my z to the power n as e to the power iota theta r whole to the power n. So this would simply become r to the power n e to the power iota n theta. So my argument basically becomes n theta. So I can simply replace it in place of theta in both my cos and sine in my polar form. Now one more important formula. This is a note that you must remember. Let's say if I have cos of theta 1 plus iota sine theta 1 multiplied by cos theta 2 plus iota sine theta 2, and this goes on up till I have cos of theta n plus iota sine theta n. Let's say if I have this type of equation, then how can I write it down? It can simply be written as cos of theta 1 plus theta 2 plus theta 3 up till theta n plus iota sine theta 1 plus theta 2 plus theta 3, and this goes up till theta n. Now again, if you were to ask me the proof of this, you can simply solve it by the Euler's theorem. If I convert this entire thing in the Euler's form, it would become e to the power iota theta 1 into e to the power iota theta 2 into e to the power iota theta 3. So since my bases are same for all these multiplications, I can write it down as e to the power iota taken common. It would become theta 1 plus theta 2 up till theta n. So that value, when written in polar form, would transform into this. So this is how De Moivre's theorem can be used to write down any type of equation. Now let's take a look at this question here. The value of this to the power 30 is. Now of course, whenever, as I've told you, whenever you have been given anything to raise to a higher power, what you'll do is you'll convert it into Euler form. So now they've given us two, let's say, equations. One of them is z1 minus 1 plus iota root 3, which is in the Cartesian format. So first, what is my task here? I'll find out my modulus z1, which would be equal to my r. So this would be equal to 1 plus 3, which makes it 2. Then I'll find out my theta, which is my argument. So my theta would be tan inverse of imaginary part by real part, so minus of root 3. So this would become so what would my principal argument become here? This would become minus pi by 3. Yes, so it would become minus pi by 3, since my argument should lie from minus pi to plus pi, right? So it would be minus pi by 3. Now let me take the other complex number where z2 is equals to 1 minus iota. How can I write this down? First I'll find out my modulus z. This would be my r. This would be root under 1 plus 1, basically root 2. And what would be my theta here? Let me call this as theta 1. This is r1, this is r2. This would be my theta 2. This would be my argument, which is equals to tan inverse of minus 1 by 1. So this is basically minus pi by 4. So now if I write both these complex numbers in the Euler form, how can they be written? On top I would have 2 times of e to the power minus iota pi by 3, and below I would have root 2 times of e to the power minus iota pi by 4, and this whole thing is to the power 30. Now I need to find out the value of this. So this would become 2 to the power 30 upon root 2 to the power 30. I've taken the constant terms separately. Now this would basically become e to the power minus iota pi by 3 into 30. So this can be written as e to the power minus 10 pi, e to the power minus 10 pi, iota 10 pi, sorry. And here we would have e to the power minus iota. This would become 15 by 2. So now from here what I can do is I'll simply convert this now into my polar form. So first of all, here I would have 2 to the power 15, and inside I'm going to have cos of 10 pi minus iota sine of 10 pi, and below what I'm going to have, I would have cos of 15 pi by 2, sorry, this is 15 pi by 2, and here I would have minus iota sine 15 pi by 2. So now simply I'll start replacing the values of cos sine in this equation. So from here I'll get 2 to the power 15. What is my cos of 10 pi? My cos of 10 pi is going to come out to be 1, of course, because cos of 10 pi is, how can I write down my cos of 10 pi as? 10 pi can be written as 5 times of 2 pi. And what is my cos of 2 pi? It is simply 1, right? So this would come out to be 1 minus, I would have iota into sine of 10 pi, 0, divided by cos of 15 pi by 2. Now this means that it is going to come in the y-axis for cos. So what is the value of cos at y-axis? It is simply 0. And here I would have a minus iota. What would be the value of sine 15 pi by 2? So sine 15 pi by 2. How can I write it down? It can be written as sine of 7 pi plus pi by 2. And what is sine of 7 pi plus pi by 2? It is minus sine of pi by 2, which makes it minus 1. So here I would have minus 1. So this would become plus iota. So now if I solve this, this is simply 2 to the power 15 upon iota. And if I was to remove the iota from the denominator, because as I had told in the previous lectures, we do not need iota in the denominator. So this would become minus 2 to the power 15 iota. I'll simply multiply iota in the numerator as well as denominator. So I would get this. And this is basically my answer. So this is how you solve questions whenever higher power has been given to you. You simply convert it into the Euler form and then solve your question. And converting into Euler form is very simple. You find out the modulus first, you find out the argument, then write it down as r e to the power iota theta. Based on that, you will be able to solve your questions.